So that's it from me. I will now start the session from Juan.
The only ground.
See you at the end.
Hello, everyone. Welcome to this webinar, PSIM Troubleshooting Tips and Tricks. This is the first webinar in our second series, or of the second part of the year. And I'm Juan Rosales, Solution Engineers for Electronics. I support PSIM along with my coworker Nikos, and which is here in the presentation. He will be answering questions in the chat. This webinar is pre-recorded, but we will be answering questions live, so feel free to drop your questions in there. So let's begin. So the intention of this webinar is to show you different simulations. All simulations have some errors and are based on real support issues we have, and these are the most common errors or issues, and I'll show you how to deal with them. And we'll cover, the first topic is how ground works in PSIM, how the probes work in PSIM. Then we're going to look at some control issues, how the AC sweeps work, how to fix some problems with the AC sweep. We're going to look at some control issues, some of them for digital control or the other one for actual control design. Then we're going to look at simulation time. Why would a simulation take too much time? And then we're going to look at switching device models and how to use them properly and how to avoid errors using them. Okay. So with that, let's begin our first set of examples I have prepared here. So first is the grounding stuff. This is pretty straightforward. It's going to be pretty quick. And so, but it happens. It's pretty common. So what I wanted to do with this inverter, this is a pretty straightforward inverter, current controlled. What I want to do here is to measure the voltage of one of the phases at the load, right? So what I do is place a voltage probe. Let me stretch it out here. Be very careful because this connection is not made. This can happen sometimes. Rename your probes, always rename your probes. This is pretty helpful for everyone. And then this is the signal I want to measure, and what I do is just click simulate. And then what I have at the output is not what I expect. Sorry. What we have here is, something that just doesn't make sense. And why is this? This is because these floating probes, these floating voltage probes, are referenced to the ground of the circuit. And the only ground in this electrical part, in this inverter, is this one here. So this measurement is not done correctly, right? The correct way of doing this would be to use a 2-point probe, like this one. We grab it from the bottom side ribbon, and we can easily connect this way, yay. And, next time we simulate this, our measurement is going to be correct. Okay, that now makes complete sense. Additionally, we could just place, this sensor here, right? Another possible error that could happen is someone might try to place a ground node here. This will effectively short this star connection with, or Y connection with, the DC bus ground, right? So this is a big no-no. So this is something to be aware of. Check your grounds. Okay, so this was the first example. It was super straightforward. Let's go to the next one. The next one is a bit more fun. So here we have Vienna rectifier. And let's simulate it and look at the output, which is supposed to be 400 volts. And we see that we're not getting anything. We are getting actually nothing useful out of this. So what's the issue here? So the issue lies here in the circuit part. And we can see that the input, these 60 hertz three-phase input, is referenced to a ground. And then at the DC output, we have this other ground, and this sensor also referenced to ground. So that's a problem. These two ground nodes, even though they look different, these are the same point, the same electrical point. So we are effectively shorting the common of these three-phase inputs and the DC output, right? We're effectively doing this, which is not good. So the first way of dealing with this is just deleting the ground that we just placed, placing correctly the sensor, and then simulating. We can now see that our output is what we expect. Now, regarding multiple grounds or multiple reference planes, if we want to use them, how would we create them? Because if we go to the library browser and we search for ground, we'll find that we have 3 different icons, let's call them, and they are all the same point. These are shorted, right? So no matter which one I place, the simulation is gonna look wrong. So what we can do to fix this is use labels. So labels allow us to just define a quick node, put it some text, and we can copy and paste it, and we can use it as a ground. So for instance, I can just rename this to DC DND, and then just place it here. Remember tip to hit tabulator to grab this, and we can just place it here, and we'll have the same effects, right? So yeah, this was very quick. Another thing to comment about grounds is the difference between the ground of an electrical circuit and a control circuit. So PSIM handles 2 types of signals, or two types of simulation domains. First one is electrical, and the other one is control, or it doesn't have a physical quantity associated to it. So these 2 are solved separately, and these grounds do not touch. Actually, these grounds are not needed. If I were to remove this one or this one, nothing would happen. Nothing bad would happen with it. But just be aware, because here we are handling, for instance, comparators, and we have some logic gates, and you might think that these are voltages, but they are not. This is just one-dimensional modeling. And yeah, the fact that these 2 grounds could be equal, something like this, doesn't affect anything, okay? This will run perfectly. Okay, so this was the beginning. It was pretty straightforward. Let's give a couple of seconds for questions and answers. And yeah, we can keep going. Okay, so the next section here is control stuff. So one of the fundamental parts that we offer for control design is AC sweeps. And AC sweeps have a very particular way of setting up, which makes perfect sense, but sometimes we can make mistakes and things will not look correctly. So I prepared this this AC sweep with the mSign method so that it is quicker for this inverter. So let's execute it and see how it looks. So pretty quick. And it looks awful. This is by any means usable. If it was your first time doing an AC sweep, it is very likely that you got something like this. At least I did. So let's fix it. Let's work on fixing, okay? And for that, let's look at the attributes here of the AC sweep block. So we have the start frequency, we have the end frequency. The end frequency here raises a flag because if we look at the switching frequency of this inverter, it is 20 kilohertz. And we are looking at an end frequency for the analysis of 100 kilohertz. And this is really not something that's not useful, because when we are generating a PWM waveform, we are essentially sampling the modulation waveform with the switching frequency, right? Which creates the carrier. And everything beyond, well, if we think about Nyquist, which is, you know, half of the sampling frequency, which in this case would be 20 kilohertz. So nothing beyond that will be useful or will actually show at the output of the inverter. So, and yeah, this is not going to be helpful. So let's start with something that's half the switching frequency, right? So 10K. And this actually is more representative of what we want, right? Just maybe a bit more detail, which I overlooked on this. So we are doing DQ control, or we are expecting to do DQ control. So we are doing a sweep on the D axis and looking at the D current at the output here, right? So that's our input and the output for the AC sweep. Okay, so let's keep on going through the attributes. So we have start frequency, we have end frequency, then we have the number of points. The number of points might be too high. We really don't need something that specific. So let's start with 100. And regarding the number of points, and specifically for the multi-sign block, there is an important restriction for the number of points. So the frequency points must be an integer multiple of the start frequency. So if we have 10 hertz and then 10K, or in this example here in the help 5K, we have points each 10 hertz, which is the start frequency. So there is a very important relationship between both, and you might want to keep it. Okay. Now the flag for points we're not gonna touch for the moment. This just changed the distribution of points, whether it is linearly or logarithmically. Then we have the source name. Let's make sure that it is the same as this one. It's pretty basic. And then the source amplitude. So the amplitude must be from 5% to 10% of the input. So 5% of 0.5 is 0.025, and 10% would be 0.5. Then the number of cycles. The number of cycles is how many cycles of the input waveform we're going to study to get the response. And then the steady state time. Here's where there might be a problem. And this is where a lot of problems come. So let's disable this. And let's put a 1 kilohertz input here. We're going to send 1 kilohertz sine to the reference and see what it looks at the output. And let's just simulate it. The best step to debugging an AC sweep is to look at the transient simulation. PSIM doesn't use average models. It will use the it doesn't use average models. It uses the Cole converter transient simulations to build an AC response. So we see that the perturbation does come up at the output, which is fine. But problem is that we were having in the attributes, we had 20 milliseconds for a steady state time, which is not correct. We see that our inverter reaches steady state somewhere more close to 40 milliseconds or maybe 60, could be a safe bet. And that's a great mistake. So every time something fails, just start playing with the sine waves, place them onto the input and see how they translate to the output. So for good measure, let's place 100 milliseconds in there. Let's simulate it. Oh, I forgot to enable this block. Let's simulate it. It takes far less, and we actually have some semi-decent results, right? So this looks far better than what we had previously. And we can actually keep improving on it. We can actually place maybe more points. Maybe we have, maybe we need a bit more of amplitude, so let's go with double what we had previously. You can see it's still fairly quick. We have a bit more definition, something a bit more smooth here. Another thing to look at always is time step. So having enough time step for the for the actual waveforms we want to look at. So yeah, always take a look at start frequency, the end frequency. We can also play with the flag for points. A steady state time is very important, so always keep that in mind. Let's see by changing the flag for points, what we have at the output. I hope it goes a bit quicker. Okay, it's almost done. It's gonna go faster at higher frequencies, so hopefully it's just gonna be a bit faster now. Maybe I overshot it with 200 points. Anyway. Okay, there it is. Much, much smoother. Okay. Now, so let's look at our next example. So the next example is this very simple buck. And what we have here is the maximum time step allowed by PSIM for 100 kilohertz switching frequency, which is 1 microsecond, sorry. And let's look at the AC sweep results. Let's see what's happening there. It's also pretty quick. But we're having a lot of noise in here, right, at higher frequencies. And so let's try and fix that. The first thing we can think of is that if we look at the original plot we are having a lot of attenuation at higher frequencies, or what, relatively higher frequencies. So we might try to put a bit more amplitude in there, right? A good trick is if you open up the sidebar here, we can save plots from this simulation and have them ready for the second one. So let's bring back amplitude. Let's bring back phase. It looks like phase is a bit better, but the main culprit here is time step. So we do need to make time step a bit lower. So let's go with our recommendation for ideal simulations in general, which is 50 points per switching cycle. So 1 over 100K over 50. This is 20 seconds. So let's place it here. Save it. Let's see what happens. Okay, it seems that we actually did a lot better, right? Specifically in the phase response, we have it so much better here. We at least have something smoother. So what can we keep doing to make this a bit better? So it looks like there's a bunch of attenuation, and that might affect everything. So we might need more amplitude. So we can place as much amplitude as we want, but we need to be cognizant of what we would be doing to the converter, right? So if I were to put something higher at 0.5 for the amplitude, I'm gonna be putting a negative signal here or a negative value here eventually, and or the current can be super low and we will put this converter in another mode of operation. So we need to be very cognizant of what would be happening to the converter if we were to place these values. But for now, let's see if this higher amplitude will actually do us any favor. Just gonna wait a bit more. There it is, and it actually did by a lot, right? So in this case, maybe we need to start thinking about the original or the first AC sweep. Because with this, we can actually define an end amplitude, right? So at lower frequencies or the low frequency range, we'll start playing with one amplitude, and then at the end, we'll start injecting more signal. And the same thing goes if we look for the other AC sweeps. The same thing goes, something similar goes with the other two. For instance, in this one, we define a pair for values, right? We have the frequency and its amplitude. So we can very easily do this also more particularly for a frequency. And the same thing goes with this one. So, but yeah, let's take a look at this with the end amplitude of 0.2. Okay. Since this AC sweep is running one simulation per frequency point, so it's gonna take longer. But we can see that the results are much, much, much smoother. And so yeah, that's it for the AC sweep examples. Hopefully you get something out of this. We're going to look at controls issues, specifically what would happen when you digitize a controller. So here we have the same inverter as last example. And I've designed a couple of controllers. This is current controlled. So I got, again, the measurements from the phase currents, got everything on the DQ frame and do DQ control. So what steps would I take to digitize this controller properly? What a lot of people do is they have a controller that they designed in the S domain or the continuous domain, and then they use this utilities S to Z converter. And here we can easily have, the proportional and the time constant. We give it a sampling frequency, and then we have a either by linear or backwards Euler, we have an equivalent for the discrete. We have a discrete equivalent, right? So, and people will just do that. So, for instance, let's just first execute this as it is and see how it looks, how the output looks like. So here, let's look at the three-phase currents. And we can see that we are actually reaching steady state. It looks fine. There's not a lot of oscillations. It works, right? It's not perfect, but it works. But if we just discretize this transfer function like the ones that I have in here, as you can see, these have the same gain and time constants. If we just place this here along with, the unit delays, and the zero order holds, let's look for them. Let's place them at 20K. We can see that when we plot the phase currents, we can see that it might not be working as nicely, or at least, or any similar to what we had previously, right? So the reason for this is because when we introduce sampling and also unit delay, specifically unit delay, we affect the frequency response of the plant, right? Specifically the phase response, which will affect our phase margin. So for instance, I created a couple of SimView files that have these responses. So we have this, let's call it continuous, that doesn't have any delays. And then let's merge a response that adds these delays for the controller discretization. So we can see that the amplitude pretty much stays the same, but the phase is quite different. The phase response is very different, and this will affect the stability of our controller. So with that regard, I took the liberty of building or of designing a couple of controllers where I included these delays and the sampling into the design beforehand. And we see, these are correct, yes. And we'll see at the phase currents that these actually, look much, much cleaner, right? So take this in mind. If you want to change from analog to digital, you need to redesign your controller. It's not going to have the same stability. Okay, now let's look at our next couple of examples. So these two examples will deal with how to debug a converter, or some examples of controllers that fail. Specifically, this one is a controller that's not doing its work, but it apparently is, right? So let's simulate it. And if we start looking at the output here, we'll see that it is reaching steady state. So this is current controlled. So we're just looking at the voltage, for instance. We see that it is actually doing its work. But if we look at the modulation waveforms, so let's look at this too. And let's look at these, what I want to, the gating signal for the boost. we'll see that we are actually having a lot of false gating. And this is because the controller is not doing its work properly. The modulation waveform has a very high amplitude, and it also has this small ripple, which is causing the comparator to actually go in and out of the output value. So it's falsely switching the gate of the transistor, right? So while it might look like it's doing its job, it is not actually doing it so. So it is very important every time you design a controller to check this modulation waveforms and to check the gating pulses to see if everything is correct. And we can actually fix this very quickly just by changing here the gain. Let's multiply it by, I don't know, 0.01. Maybe that helps. And we'll see that we are reaching the same steady state. But now, if we place attention to the modulation waveforms, we now have something that makes sense. We don't have false triggering of the comparator, so everything is fine here. So this is something that could happen. It actually happened to me once. So yeah, just be on the lookout. The next example, we return to our inverter here. Next example is saturating our modulation scheme. So if the modulation waveform is of higher magnitude or amplitude than the carrier, we're gonna have some issues, right? And in this case, let's just simulate it and see how they look. So let's look at the modulation waveform here. So we can see that there's a couple of details in there, and we can see that the signal is very noisy, and this can happen a lot. And some might come to support and say, hey, these waveforms look super weird, everything is noisy, what's happening here, right? So in this case, it is a typo. So if we look at the PI controllers, both, on the gain, I forgot to place this micro suffix or prefix, and this actually fixes it. So play around. If something happens to your modulation waveforms, pay attention to your controllers, right? It's very likely your controller is not doing its work. On another occasion, a user had its PI controller parameterized, so they had variables here, and one of the controllers had them, but the other one didn't. So they were essentially two different controllers working very differently, and they had a very noisy modulation waveform. And the fix was just to just copy and paste this one here, right? Or have the variables be in the correct place, right? So always be careful with that, because that waveform, the previous waveform we saw, actually looks very troubling, right? It doesn't look nice. So we might consider reaching out to support very quick. So yeah, this now is fixed. Okay, so with this we end the control issues part. Let's wait a couple of seconds or maybe half a minute for questions and answers, and then we can transition to the last part of the webinar. Let's close this. Again, my coworker Nikos will be answering the questions in the chat. So yeah. Okay, so let's continue. The next section is, why is my simulation taking too much time? And then how can we either make a simulation run faster or how to perform simulations more efficiently, considering time. And the first example we have is this buck converter. This is the simplest thing you can have. Well, not the most simplest thing you can have, but maybe the most simple converter you can have here. And the switching frequency is 50K here. And we have the correct time step, which I previously calculated, of 2 microseconds. we simulate it, we have this window that tells us that the time step has changed to 10 nanoseconds, and we click OK, and then our simulation is just going to take a while. And why is this happening? In this particular case, it is happening because in the frequency source, or in the triangular source, we placed a duty cycle of 0.99999. What this does is it forces PSIM to choose a time step to accommodate this duty cycle, because PSIM won't do a rounding to 1. It won't do that. So it will change the duty cycle to accommodate it. So a good fix is to change this to 1. But let's not be mistaken. This simulation is actually running, and there's nothing wrong with it. So one might be confused as why is this failing, right? So it is as simple as this. So let's stop this because it's just not going to finish. We see that the waveform is correct, and if we look at the gating waveforms, they are going to be correct. But to fix this and to make this quicker, just need to place this onto 1, and then change the time step to the original one. That's right. Which I didn't do. To fast, almost instantaneous, right? So this is a very interesting source of issues where when our simulation is taking too much. So PSIM will not only look at sources, we'll also look at dead time, or really any predefined period of time that PSIM is aware of, right? That we explicitly place into the circuit. So an example with dead time is this full bridge resonant LLC converter. So let's place a dead time of 0, and let's use this time step that we've chosen. We can see that it takes a reasonable amount of time to solve, and we can see that the output is what we expect. Everything looks fine. This has the print flag here. The print time here changed, but it actually works, right? There's no issues there. It is pretty quick. And then if we place dead time, maybe by accident or consciously, now the time step is going to be dramatically lower, and the simulation is going to be so slow. And it's not necessary, right? So when thinking about using dead time, be aware of how or of when to use it, when it is absolutely necessary and when it is not, because it will make your simulations slower. Okay, so let's stop that for a second. And let's look at another topic which is pretty interesting, and this is found here on the simulation control. So how would we make simulations run a bit faster? And this would be by using the dual type step. So PSIM by nature is a fixed step solver, and there's an alternative way of simulating with a dual step. What this does is that it will select another time step when we transition, when we have a switching event. So every time a transistor or a diode turns on or off, the time step is suddenly reduced by a ratio, which we select in here. So let's select 10 for now, and let's look at the simulation, and let's leave the dead time as it is to see if it, okay, time to ratio has been changed to 20. We'll see that the simulation is taking much less time. We are getting away with dead time, and we'll have a full simulation at the end. And if we look at a couple of gating waveforms, like this one here, and we enable some markers, we'll see its behavior, right? We'll see that in a switch transition here, we'll see that the density of data points is higher when we reach a transition, right? So this is pretty helpful when you're dealing with those sorts of things. The next method of maybe not making a simulation faster, but at least being more efficient with the way we simulate, is by using the load and save flags. So the load and save flags are pretty cool because they allow us to simulate at different time steps, and then use all of those simulations. So maybe let me rephrase. So what it allows us to do is we can run a simulation at a lower time step, at a higher time step, sorry, just to get to steady state. So our simulation is pretty quick. And then, for instance, if we're doing conducted EMI analysis where we are interested in high frequency harmonics that need a more detailed time step, then with the load flag, we can pull those results from the higher time step simulation and use them as a starting point for the next simulation, right? So let's do that. Let's do that for a second. Let's actually first simulate it. Let's do here, and let's do 10 milliseconds, and let's use this time step, which I believe is okay. So we can see it is pretty quick, and our output voltage should be fine. Everything is fine. So let's pull up maybe some voltages here, and we'll see that we might not have a lot of detail in here because the time step is not enough, right? So to use the load and save flags in this simulation of 10 milliseconds, we're going to put the save flag to 1, load flag to 0, simulate, wait for it to be done. It is done, all good. And then we go back to the simulation control. We change the load flags to 1, the save flags to 0. And then we put a bit more time to the simulation. Let's put 2 extra milliseconds, and then let's change the print time to just 10 milliseconds so that we can see the results from 10 milliseconds onwards. And let's change, maybe add a couple of orders of magnitude, maybe just 1 order of magnitude for the simulation time. So as we can see, we are simulating less time, but our simulation efforts are more effective because what happened here? Load flag. Let's do this again. Okay, there it is. So now we are simulating from 10 milliseconds towards 12 milliseconds with much more detail. And if we now look at, for instance, the voltage across one of the transistors there, we're going to have much more detail, right? And we can go even further because we can see that maybe that's not, super, it's not as useful as we expected. So for instance, let's remove another order of magnitude. Let's just use 1 millisecond of simulation. And this is, of course, slower, but it's much faster than simulating the whole 11 milliseconds at this time step, right? That's not a super effective use of our time, maybe. So yeah, let's wait for it to be done and look at the results. Okay, perfect. Now we can see much more definition here on the oscillations here. Okay, so that's pretty nice. That's a pretty nice trick. Additional things you can do with the load and save flags is to change the passive values of certain components. For instance, if I want to decrease the load, make the resistance be twice its current value, I can do that and the simulation will work. Something that I cannot do is to add new components to the simulation, right? So I cannot just place another resistor or another capacitor. Like, so easy. And we'll maybe check the results here. Let's look at this. So we can see that that everything is working, really. The dynamics look a bit different to what we had previously. But we can keep doing this with all of our passives. But again, what we cannot do is, if I place this resistor here, and start simulating, actually PSIM won't detect an error, but things just won't look good, right? Which in this case means that the voltage is just dropping in there. So yes, that's it for this section. Well, it's done. I believe it didn't have any issues with this. That's interesting. But yeah, just to be careful, just don't go removing or adding components when using the load and save flex. Changing values, that's fine. Okay, so I'm gonna give maybe 30 seconds for some questions and answers. Nikos will be in the chat. So yeah. Okay. Okay, so some final points. Let's go back to the slides for a second. Let me actually, okay, perfect. So just final thoughts. Model selection. So switch model selection, select the correct model for the task, and you'll get the results that you expect. For instance, so using ideal models for controls design, topology design, not for EMI, not for whatever other stuff. Maybe you would be thinking about doing extracting losses with these switches. Don't do that. Same goes with the thermal. Use thermals just for thermal design, thermal simulations. Don't expect being able to multiply the voltage and the current waveforms to get the switching losses. And then using non-ideal switches specifically for EMI and similar applications where we want that level of detail, right? Getting the transitions, getting parasitic interactions, oscillations, and all of those sorts of phenomena. Don't use them to calculate losses, and I'll explain why in a second. So for loss calculations, these might not be the best model, specifically because when modeling, there might be a small delay in comparison to the actual real thing or a spice. So in this case, we have a comparison between a level 2 model and the spice waveform. So we can see that the slopes, the actual shape or the harmonic content we can match. What we cannot match is this timing event or the timing of that, which will affect loss calculations, right? So yeah, please stick to thermal models for thermal loss calculations. That's the best model we have for that. And yeah, so let's look at thermal module issues also. So it is very hard for these for the thermal module to have some issues, really, but the few times that it has, it kind of looked like undesired spikes, like these ones. And how to fix them is pretty straightforward. We go back to PSIM. Let me open up one of our thermal examples. I have this is the scene view. There it is. So to deal with this, something very nice that we can do is inside the model, there is this flag where we can skip the voltage, the update of the voltage across the device. So these thermal models, as you might know, they update the drop across them during turn on. So by placing this from 0 to 1, it will turn off that feature. It will still calculate losses according to the turn on voltage or the turn off, turn off voltage and also the currents. It will still do its job, but it won't update the drop across the device in the simulation. Okay. So let's go back to the slides for a second, just to deliver some final thoughts here. Okay, so thank you. Thank you very much for attending. I hope you had something useful, you got something useful out of this webinar. These are pretty common issues that we face. This doesn't mean that we don't want you to reach out to us whenever you face something. On the contrary, we're open to help you. We just wanted to give you more tools to debug your simulations. And yeah, so that would be it for us. We will stay for a while, a bit more, to answer more questions. And if there's none, we just let you go. Have a nice day, everyone. And thank you for coming. Thank you, Nikos, for being here. And yeah.
Thank you everyone for attending this session. In case you have any questions, please ask them in the chat. Thank you for the comment. There is some nice feedback for you, Juan. Good presentation. Several important points about the simulation were clearly explained. This is why we did this in the first place, right? So it's always good to have a resource for tips and tricks. This is something we also do while supporting our users. So please feel free to create support requests. Sometimes it's for something really simple, but even sharing a schematic with us, we can take a look and we can see a lot of things that we as PSIM expert understand that can be further enhanced, and we can let you know. So contacting support is another way to get these tips and tricks right away, even if it's not about the original problem that you contacted us for. So I don't see any other questions. I'll wait for a couple of minutes. So where to find the recording? So the session was recorded and the recording will be uploaded on YouTube in a few days. So you will be able to see it afterwards as well. By the way, all the webinars from the series we are uploaded on YouTube. This happens every the first Thursday of every month. So thank you everyone for attending. I don't see any other questions. See you in the next one. Have a nice day.